interactions in the genetic model. Now I simulate a situation where you not only have the genetic mean effects, but also have the interaction effects in both models, both mean effect and genetic interaction in the model. So this is the number of repeat simulations I get with this sample size. Actually, for the simple examples, this number was used. So the comparison I did here was the marginal A. A here means the correction, adjustment. C here means composite approach. Okay, for the conditional approach, with this, and also this we do the joint analysis. This joint analysis is actually just a version of this conditional analysis. Remember, we do two conditional analyses. One is using the primary outcome conditional on secondary outcome and genetic and environmental effects. The second analysis is use the secondary outcome conditional on the primary outcome, the genetic marker, and the environmental effects. So if you combine those two together to perform one analysis, this is called joint analysis. The effects is virtually the same, but theoretically, this is better because we can calculate the variance relatively easily. Okay? If you do two conditional analysis, there is a glitch there, which makes compute the correct estimate, the variance for correct estimates harder. So this is why the conditional analysis, joint analysis were done. Okay. Here is the simulation results. R is the baseline prevalence rate. We simulate for 1%. Now I do not present a picture here because I want to show you that the variance as the average of the simulated variance and the estimated variance somewhat close. And also, if you look at the variance here, you see different approaches, different corrections. The variance doesn't change much, right? Very close to each other. And for some of those approaches, I put a black here, means the variance is not easy to calculate here. Okay, look at this one, especially. This is joint approach. The correction, this is bias we have. If you do not correct, then you have this many bias. Okay? For conditional, for the interaction effects, the bias reduced is not substantial, but if you look at this one compared to this one, then it's comparable. Okay? This is assumed to be an accurate analysis. Okay? It's quite comparable. Okay? So this is for R equal to 1%. For R equal to 10%, okay, the bias is a little bit worse here. If you look at this, but the variance remains pretty much similar. Okay, for 25%, okay, you see here. The bias is even smaller. This is maybe the artifact. Okay, it's pretty much close to this one, but the bias correction is substantial here. I also simulate the power, the size of and power of the test. Remember, I list there. Here, those test 1, test 2, test 3 basically set for different prevalence rate. Here, this prevalence rate is the true prevalence rate I used in simulated data. When I perform this test, I pretend I do not know this truth. This one corresponding to, you assume this prevalence rate is 0. This one assumes the correct prevalence rate. And this one assume 10% prevalence rate. And this one, 25% prevalence rate. The last one is 0.5. Okay? So here, those boulder-faced numbers are supposedly to be the correct number. Here are supposed to be 5%, but they are close. Okay? Those are the powers. But it's interesting to look at the neighbors of those numbers. If you get a wrong prevalence rate, then you see that the size is not that far away. Okay? So I should mention this one is for testing both interaction and main effects are 0. And this one is for testing the interaction is 0. Okay? So that basically says if the baseline prevalence rate is a little bit off, then you are doing okay in terms of controlling the top 1 error. And if you look at the power, you will see that the power is also relatively fine. Of course, sometimes you get more power. That's just by chance. So if you compare the lowest power in the neighborhood, then you see that it's not that a big difference. Okay, in this neighborhood. Okay. Here is the summary of the approach we used. Okay. Basically, when we apply the correction approach to marginal analysis, the performance is not as good as correction applied to conditional analysis. Okay. This is seen from the simulation study. Theoretically point of view, this is because when you apply it to a marginal analysis, you actually do 2 approximations. One is for the numerator, the other is for denominator. So that makes you the approach a little bit perform worse than conditional approach. Conditional approach just approximate by once. Okay. The correction approach by using compensator perform better to simple correction approach. Okay. But the difference is not that much. Okay. In view of the substantial computational burden you need to deal with, then this direct correction is somewhat favored. Okay. So in practice, we can do this correction to the joint analysis. Okay. The reason is because of variance estimate. When you do inference, it's easy. Okay? And also the joint analysis isn't hard to do. It's quite straightforward. To apply this to the example we have here, for this high density lipid protein level in plasma, this is primary phenotype. And the secondary phenotype we analyze here is the low density lipid protein level in plasma. Okay. We could do the other secondary trait, but I show you only this one here. This sample design, remember, depends on the high density lipid protein, age, gender of the subjects. Okay. So we concentrate on 60 SNPs that appear to be associated with primary phenotype. Why we do that? Because for all other SNPs, this correction isn't really doing much, because if the primary outcome does not associate with SNPs, we can somewhat assume that the correction if it is there, should be relatively small. So what we do here was to use both as dichotomous variable, which was used in the data set. Okay? So we performed the logistic regression with now age and gender as the covariates. Here, age and gender are both